Hi everybody. Well, I advertised when I made the course planner. I was going to make a couple handouts on cyclic groups, and what you're looking at in front of you is essentially that. Now, the first few pages of this we already worked through a few in our last meeting, and basically I just say, okay, here's the definition of a group. Remind you we can use addition or multiplicative notation. Zn's an additive group, Un's a multiplicative group. The automorphisms of Zn is a group of composition, right? And then I defined, we can define powers. We have laws of exponents, these things to work with, right? Then, what did we do? Then I mentioned to you a couple of examples. Zn, of course, is an additive group. Un's a multiplicative group. I proved that Un forms a multiplicative group principally through arguments involving like the division algorithm and Bezout's theorem here, right? So we did that. Then I started talking a little bit about the order of an element and the order of a group. Of course, the order of a group is the number of elements in the group. It's either finite or it's infinite, and I defined the order of the group of units to be the Euler phi function of n. That's the number of integers between 0 and n, 0 included and not included, which are relatively prime to n, right? And we looked at a number of examples to try to give you formulas for that, right? First of all, obviously very important, if it's prime, all the numbers up to p are relatively prime to p, which gives us the formula that phi of p is p minus 1. For example, phi of 5 is 4. And then we started looking at like powers of primes, and we noticed that we had to throw out multiples of the prime, which led us to the formula, for example, phi of 9 equals to 6. And then we saw phi of 25 was, well, 25 minus 5, which was 20, right? And I think I failed to write that down here. Let me add that in there. So this this list right here shows you that phi of 25 equals to 25 minus 5, which is 20. There are 20, count them, 20 numbers which are relatively prime to 25. Modulo 25, of course. All of this is done using modular arithmetic, which of course we talked about before, and is the primary tool you need to solve your mission 2. And then, of course, we had to throw out, multiples of 3 for this one, and we had that phi of 27 is 27 minus 9. All right, so we saw a pattern, some further examples. Euler phi function, powers of 2, works pretty much the same, actually, in terms of the counting here. What's interesting later is we'll see that the structure of un, when n is a power of an even 2 to the n, it's a little bit different than when it's an odd power to the n. We'll see that eventually. Anyway, moving on with my very fast review of a material we've already covered. Just trying to get it all out there all right. And I will scan these and put them in course content. It's going to take me a little while. There's a lot of pages. Anyway, so if G is a group, H is a subset, then we have a subgroup. If the operations of the subgroup, if the operations of the group restricted to the subgroup, give you a group once more. Of course, we have the subgroup test. It's enough to check that 2 elements of the subgroup are again in the subgroup in the sense that A, B inverse is in the group. Or you could separately check that it's closed under the product and the inverse. And of course, these inverses become minuses if we're in an additive group. All right. So then that, of course, brought us to the definition of the cyclic subgroup generated by an element, right? So if it's multiplicative, then we're looking at powers, all integer powers. If it's additive, we're looking at multiples. In both of these cases, this includes both, like, positive n and also negative n for inverses, right? And if you have a subgroup and there exists an element such that it is generated by that element, then it's said to be a cyclic, or sometimes people say cyclic, but cyclic subgroup of G. Theorem. A cyclic subgroup is a subgroup. So we proved that, right? Essentially laws of exponents in the subgroup test theorem, not a big deal. And then I started talking a little bit more, sort of flash forward, here's what we're going to prove next lecture, right? I'm actually not going to prove that, but my bad. I think you saw it in your course, so I'll let it stand at that. But if H is a subgroup of G and G is finite, then the order of H divides the order of G. This is Lagrange's theorem, right? Which is proved by sort of just partitioning the group into little pieces. And we have other theorems that I have written here, and I think we're going to get back to all of those shortly, so I'm not going to go over them again. Now, let's see here. I should also remind you the definition. If you have an element of the group such that the group is generated by that element, then that group altogether is called a cyclic group with generator A. All right. And we have theorems. For example, and these theorems I have proofs of, I believe, in the upcoming pages. So this is kind of a, this whole page is a, foreshadowing. But these are theorems that we kind of want to learn, It's actually more important to me, for you students of number theory, that you are aware of the results and able to apply them, as opposed to reproduce some of these proofs, because I'm going to go over a lot of proofs here, and like a lot. And almost all of the proofs are essentially applications of divisibility theory or Bazou's theorem and definitions. And while those are interesting, I think really the heart of this number theory course is I want you to understand the structure that the theorems are saying, and I want you to be able to do calculations. So in as much as the proofs are helpful towards that end, you should focus on them, all right? But I feel obligated to show you the entire proofs, because I think that we should have a discussion about cyclic groups from beginning to end, that I put all the cards on the table, and that's what I'm doing right now. I'm trying to put all the cards on the table. All right, so, and hopefully I have some useful examples in here for your homework also, especially Mission 3. I have some examples later on in this handout, which are pretty much your homework problems. Anyway, so if G is cyclic with generator A and the order of G is n, then G is also generated by a to the power k when when n and k are relatively prime. So for example, if you had a group A, the order of the group was 10, then you could use 1, 3, 7, and 9 are relatively prime to 10, which means that either A works, A cubed works, A to the 7th serves as a generator, and A to the 9th also serves as a generator. In a group of order 10, you have 4 choices for your generator. All right? 4 choices. Corollary. The number of generators for G is actually given by phi of G, because remember, phi of G is the number of positive integers relatively prime to the order of the group. So here, application, if H is a subgroup of G and the order of H is 8, since phi of 8 is equal to 4, there are 4 generators in H. Then I mentioned we should talk about the fundamental theorem of cyclic groups, and we'll do that. Let's see here, 7. I gave you this example, I think, is kind of the parting example in Lecture 1. Apologies for this very long review, but I think it's necessary. Again, this first 7 pages I have expanded into basically 8 hour plus lecture before, so this is all a review of things I've said in class at this point. So Z20 is generated by 1, of course, and essentially you can take 20 and divide by its divisors. That gives you generators of subgroups. Of course, the most silly one is 20 over 20. Well, it's not really silly. 20 over 20 is 1, and well, the Z20 is a generator. Of course, there are other choices, right? What else is relatively prime to 20? Well, 3, 7, 9, 11, 13, 17, 19, all of those would generate Z20. And then if you divide by 10, you get this subgroup generated by 2. The evens, you get the subgroup generated by 4, the multiples of 4 like this. Subgroup generated by 5, multiples of 5. Subgroup generated by 10, that gives you 2 things, right? And by the way, there exists a unique cyclic group of order n. So like when I see a cyclic group with 2 things in it, I know it's isomorphic, meaning that there exists a one-to-one bijection which preserves group operations, right? Like that. So anyway, that led me to the question, what about UN? Is UN cyclic? What can we say about the structure of UN? What does it actually look like? I was like, well, no, it's not cyclic all the time, but there's a lot we can say, and let's try to work on saying that. That's our ultimate goal in this series, this lecture here, is to get to the point of explaining what we can say about UN, in fact. Right? So, here we go. The genuinely excuse me, new material. Now time for me to cough. Alright, so first order of business. There exists a unique cyclic group of order n, up to isomorphism. Alright, the proof is pretty straightforward. You take 2 cyclic groups of order n, you suppose x and y are the generators, and you define a mapping from one to the other in terms of phi of x to the m equals to y to the m. And there's no loss of generality there because, of course, we're assuming that these are cyclic groups. And just to get us to wet our whistle, notice that it sends the identity to the identity. That's a good sign. And in my proofs in this lecture, I will sometimes use E sub g and E sub h to denote the identity in G versus the identity in H. Now, I do that to a certain extent in my notes, but if you read my abstract algebra notes, you'll find that I just use E for the identity in all groups because distinguishing EG and EH, it does get kind of old after a while, I'll be honest. Anyway, here it is. So if we take a product of phi of AB, well, that's phi of x to the m, x to the n, which by the laws of exponents is phi to the x plus n, which then by the definition of phi is y to the m plus n, which then by the laws of exponents is y to the m times y to the n, which then, tracking back with our definition for phi again, is phi of x to the x to the n, which then is phi of a, phi of b, which proves that phi is a homomorphism, right? And then to see that it's not just an homomorphism, but in fact it's bijection, it suffices to show that it's surjective. Let's see here. Why is that? Well, this is a finite set. So if you have a mapping from one finite set to another, if it's onto, it's automatically one-to-one, right? Now I think I actually give you a proof of surjective and injective here, but really that was redundant because this is a finite set. And if you can prove a finite set has a mapping which is onto, it's automatically one-to-one. This is just set theory. Observe, x to the n is in G, then that means phi of x to the n is equal to y to the n, which is equal to z, but z was arbitrary, therefore psi is surjective. And finally, if phi of a is equal to phi of b, that gives us this, which gives us that, which then multiplying by y to the minus n on both sides gives us this, right? Thus, m minus n has to be equal to 0, and that follows m equal to n, which then tells us, tracking back, a equals to b, which is to say psi is injective. In summary, there exists a unique cyclic group of order n as claimed. So I will sometimes talk about something and say, oh, well, that's the cyclic group of order 7, as if that's like the end of the story. And it is the end of the story up to notation, right? You could use an additive notation, you could use a multiplicative notation, but the fact of the matter is there is just one cyclic group up to isomorphism of order 7. Alright, so next order of business, and I really should add numbers to these. I'll try to add the number to this before I post the PDF, okay? I wanted to tell you where I found those in my notes. My notes are largely inspired by Galilean's abstract algebra, and this is from a course really that I taught in 2015, 2016, somewhere in there. But anyway, here it is. Let G be a group. This is the technical linchpin for a lot of what follows. And it does kind of give you some guardrails for how we do calculations in a cyclic group. But here it is. If we have a group and A is in the group, if the order of A is infinite, then I not equal to j implies a to the I is not equal to a to the j. All right. So this would be like integers, right? N, if you have n times 1 equals to, if you have I times 1 equals to j times 1, and I is not equal to j, well then I is not equal to j. I mean, it's hard to even say. But my main infinite group to think about is integers, I suppose. But anyway, there are others. Okay, so if the order of A is n, then the cyclic subgroup generated by A, 1, A, an minus 1. What I'm trying to say here is that this is a list. It has n things in it, just n things. And here AI is equal to AJ if and only if n divides I minus j. All right. So we get equality only if I and j differ by like a multiple of n. All right, so the proof. First of all, if the order of A is infinite, suppose for I not equal to j, we have AI equal to AJ. Without loss of generality, we can suppose I is greater than j multiplied by a to the minus j on one side. We get a to the I times a to the minus j, which is equal to a to the j, a to the minus j, which is equal to e. Thus, a to the I minus j is equal to e. Thus, the order of A is less than or equal to I minus j. Oh no, that's a contradiction because we said the order of A was infinite. Therefore, AI is not equal to AJ. So there's one part of it down. Next up, if the order of A is n, for some n, suppose AI equal to a to j, for some 1 less than or equal to j less than I less than n, again multiplied by a to the minus j to obtain a to the I minus j equal to e. But notice that j less than I less than n implies that I minus j is less than n minus j is less than n. Hence, a to the I minus j is equal to e for a power less than n, right? Which contradicts the order of A being n. Therefore, AI not equal to AJ for 1 less than or equal to j less than I less than n. So that assures us that there's no redundancy in this list, right? And then finally turning to this part of the claim, right? Suppose k is an integer, then by the division algorithm there exists q and r in the integers such that k is equal to qn plus r, where the remainder, of course, is between 0 included and n not included. Observe that a to the power k is a to the qn plus r, which is a to the qn times a to the r. But by laws of exponents, we can pull the power q out like so, and that gives us a to the n to the q times a to the r. But a to the n is e, so e to the q is e, e to the q is still e, and that leaves us with a to the power r. Therefore, for 0 less than or equal to r less than n, we have allowance for r going from 1 all the way to n minus 1, and in fact, our list is as advertised. Right? And then finally, I should say finally, the last bit of the theorem here, below this line, is suppose AI, let me try to be careful not to lead over to the next page here. Oh, so many pages. Yowzers, bowsers. All right, so suppose that AI is equal to AJ for some I and j and z. Well, then you can multiply by a to the minus j as to obtain a to the a minus j equal to e. Then we can apply the division algorithm, again, to obtain q and r such that I minus j is qn plus r. Hence, e is equal to a to the minus j is equal to a to the qn plus r. But then by the laws of exponents, we have a to the n to the q times a to the r, which of course is e to the q times a to the r, which is a to the r. Therefore, a to the r is equal to e. But since r is less than n, we must conclude that r is equal to 0, otherwise we contradict the fact that the order of a is given to be n. Therefore, I minus j is equal to qn, which is to say that n divides I minus j. And conversely, if n divides I minus j, that means I minus j is a multiple of n, and we can quickly calculate that a to the minus j is equal to e, which means that ai is equal to aj. And so there you have it. No particularly difficult part to this proof. I have certainly made my abstract algebra students be responsible for proving this, but I don't foresee myself making you guys prove it. I want you to understand the theorem, all right? So I probably should stop saying I'm not going to make you prove it, I'm not going to make you prove it, because at some point I'm going to make you prove something, you know? But anyway, I will try to be, when we get to the point of having a test that might have a proof on it, I will try to be rather explicit about, I expect you to be able to prove this theorem, all right? So we'll just make that agreement with each other, okay? Now, page 10. Corollary. For a cyclic group of order n, we have ai equal to aj if and only if I is equal to j plus nk. So that's basically how it goes, right? Corollary. If G is a group and A is an element of G, then the order of A is actually the order of the subgroup generated by A. That's very important. That connects the order of the element to the order of the group generated by that element. We use that all the time. Corollary. If G is a group and A is an element of G, with the order of A being n, well then if A to the power k is equal to E, it must be that n divides k. K has to be a multiple of the order of A if A to the power k is equal to E. Alright? Now, proof is pretty simple actually, because it's the corollary, right? A is in G, the order of A is n, and A to the k is equal to E, and then A to the k is equal to A to the 0, right? But then n must divide k minus 0, hence n divides k. Yay. Alright, that wasn't bad. Theorem. Theorem. If G is a group, and A is an element of G, and the order of A is n, and k is an element of n, then the subgroup generated by A to the power k is equal to the subgroup generated by A to the greatest common divisor of n and k. Alright? So, you know, obvious corollary here, if k and n are relatively prime, then A to the k is equal to A to the 1. In other words, you get another generator, right? But this is more general than that. More than that, A to the power k, the order of that element is n divided by the greatest common divisor of n and k. I've put a little underline with green and star here because I'm going to prove that part of it on the next page. All right. So here we go. Assume G is a group and A is an element of G with the order of A being n. Let k be a natural number. Let D be the greatest common divisor of n and k, right? Well, then D is the divisor of k. Hence there exists an integer such that k is equal to CD. So suppose x is an element of the subgroup generated by A to the power k. Well, then there exists y in Z such that x is equal to A to the k to the y. A to the ky, if you will. Observe that x is equal to A to the ky is equal to A to the z dy, because I have assumed that k is zd. But then rearranging by laws of exponents gives me that A to the power d to the power zy is an element of, well, that's equal to x, but that's also, by definition, a power of A to the d, which is to say that it's in the subgroup generated by A to the power d, which of course is GCD and nk, right? This is literally A to the d, alright? Thus, the subgroup generated by A to the power k is a subset of the subgroup generated by A to the GCD of nk. Alright, so we're trying to prove these are equal, so that's half the containment. Conversely, suppose you've got an element of the subgroup generated by the GCD of nk, then that means that W is A to the D to some power U, which is A to the DU. So then by Bosu's theorem, there exists P and Q such that Pn plus QK is equal to D. Thus W is equal A to the DU, which I replace by Bosu's this, and then by laws of exponents we have A to the Pn times A to the QK, but that's A to the n to the P, which of course A to the n is by assumption E here. And so we have E to the P, which is just E, and we have A to the QK, and that simplifies down to A to the K to the QU. But of course that manifestly shows you that W is an element of the subgroup generated by a to the power k. Hence, this is a subset of that, and we conclude that they're equal. All right, so that brings us to the starred portion of that theorem. So continued here. Now, it remains to show that the order of a to the k is n over d. Remember, d is the GCD of nk here. So observe that a to the d to the n over d. Now that makes sense because remember, d is the greatest common divisor of n and k, which means that n over d is actually a whole number, right? And anyway, so a to the d to the n over d is equal to a to the n by laws of exponents, and that's equal to e. Hence, the order of a to the d is at most n over d, because we just showed that the n over d power gives us e. And if 0 was less than I was less than n over d, well then we'd have di is less than n, and hence a to the d to the I would be a to the di, which is not equal to e, since the order of a is n. Therefore, it must be that we don't have this, but we have, in fact, the a to the, we don't have less than, we actually have equality. The order of a to the d is n over d. Hence, the order of a to the d is the order of the subgroup generated by, of course, the GCD of nk. That was just our definition of d. And this is the fact that the order of the element is the order of the subgroup generated. And finally, that gives us that the order of a to the k is n over d, which is, as claimed, n over GCD nk. So there's that. All right, corollary. Corollary. Again, getting all the cards on the table. If the order of a is n, then the order of a to the I is equal to, the subgroup generated by a to the I is equal to the subgroup generated by a to the j, if and only if the greatest common divisor of n with I is equal to the greatest common divisor of n with j. All right. So here's the proof. You let G be a group, A an element of G, the order of A being n. Then by theorem 1.6.15, which is the one we just proved, AI is equal to this, and HA is equal to that. Thus, the GCD of Ni is equal to the GCD of Nj implies that the subgroup generated by a to the power I is equal to the subgroup generated by a to the power j. And conversely, if these are equal, that means that their orders are equal. Thus, by theorem 1.6.15 again, the order of AI is n over this, order of AJ is n over that. But since these are equal, those are equal, and then that, of course, immediately implies that the GCD of n with I is equal to the GCD of n with j. Right? So this actually gives us a lot of insight as to, if you've got a cyclic group and you want to look at powers of the generator, how can different powers generate the same groups, right? Well, you can test what the outcome is going to be by judging the relative, by finding the greatest common divisor of those powers with respect to n. Like, let's see here, like if you had a group of order 10, and you were looking at a to the 4th and a to the, let's see here, a to the 8th, I think the GCD of 4 and 10 is what? 2, right? What's the GCD of 8 and 10? I think it's still 2, right? So a to the 4th and a to the 8th, they're going to be the same subgroup if you generate with a to the 4th or a to the 8th in a group of order 10. Now the order of the group matters, right? It's always measured relative to the size of the group in which you're working, how these generation comments work. Corollary. If the order of G, if G is cyclic with generator A and the order of G is n, then G is equal to a to the k. In other words, G has another generator a to the power k, if and only if the greatest common divisor of k and n is 1. All right. Proof is pretty straightforward. Assume G is A, generated by A. Then by the corollary, right here, this guy, by that corollary, a to the k is equal to a to the 1 if only if the GCD of nk is equal to the GCD of n1. But of course the greatest common divisor of n and 1 is 1, thus the greatest common divisor of n and k must be 1. Anyway, so there's that. And of course, this is actually like, really, really critical to our thinking. If k is in Zn, then k serves as a generator of Zn if and only if it is relatively prime to n. So that tells you how I can find generators of Zn. I look for relatively prime candidates, right? That's it. The generators of Zn are exactly those things which we find in Un, in fact. All right. Here's an example. All right, so U14, we can see that U14 is cyclic by direct calculation. So if you look at powers of 3, you'll find out that you exhaustively generate all of U14, all right? Namely 1, 3, 5, 9, 11, and 13. And when you look at the powers of 3, it goes like 1, 3, 9, 13, 11, 5, and back to 1 again, right? So the powers of, if you list the powers of 3, they're not in that order, right? But it does fill out that list. And so we could see that the order of U14 is 6, which means that, well, think about it, 1 and 5 are relatively prime to 6, which means we could use 3, or we could use 3 to the power 5 as a generator. And 3 to the power 5 works out to 5 in this case. So either 3 or 5 serve as generators for the cyclic group U14. Comment, not every UN is a cyclic group. All right, well, anyway. Another example here, just in terms of generators. If we have a cyclic group of order 5, then of course the order of A is 5, A to the 5th is E, and we can look at, like, here's the subgroup generated by A, subgroup generated by A squared, subgroup generated by A cubed, the group generated by A to the power 4, and all of these are the same because, of course, 2, 3, 4 are all relatively prime to 5. So in a cyclic group of order 5, you have a choice of 4 generators. You give me any one of them, give me any generator, well, I can tell you that you can take that generator, you can square it, you can cube it, you can fourth power it, and all of those will also be generators for G. And this ultimately, of course, remember, we can judge the number of generators by looking at phi of 5. Phi of 5 is 4 in this case. What page was I on? 12. It's 13. Another example. Another example here. If the order of G is 8, then we could use, let's see here, well, A squared, I mean, we could try it, right? It gives us E, A squared, A to the 4th, A to the 6th. That's not going to be all of G, is it? Because the order of G was 8. On the other hand, the GCD of, here I'm pointing out, I know this is a group of order 4, so like the fact that the GCD of 3 and 4 is 1 means that I could also take the third power of A squared and also get a generator. On the flip side of things, we could look at the GCD of 8 with 2, and of course that's 2, and the GCD of 8 with 6, it's also 2. That's another reason that this and that are equal, going back to that theorem we just went over. Now, A to the power 4 gives us a subgroup of order 2, and of course, if you just look at the subgroup generated by E, you just get E again. In contrast, you could use A cubed, A to the 5th, or A to the 7th to generate the totality of the cyclic group of order 8. Alright, so this finally brings us to the fundamental theorem of cyclic groups. fundamental theorem of cyclic groups basically gives you a breakdown of what are the possible subgroups, what to expect in subgroups of a cyclic group, and here's what we learn. If G is generated by A, a cyclic group, then number one, a subgroup of G is cyclic. If the order of G is n and H is a subgroup, then the order of H, if it's K, then that K must divide n. In other words, the order of a subgroup of a cyclic group must divide the order of the group. Of course, you say, well, that's just Lagrange's theorem. Indeed, it is. But we actually can give a direct proof here of that. But there's a little bit more. If the order of G equals n and K is a divisor of n, then H equal to a to the n over k is the unique subgroup of order n over k in G. In other words, in a cyclic group, if you have a divisor, there is a subgroup, and there's just one subgroup of that order. That's a very useful criteria in judging something not to be a cyclic group. See, because if you find a group and it has two groups of order 5, two subgroups of order 5, then you can justly see that that group is not in fact a cyclic group because it didn't have a unique subgroup of order 5. All right, so here's the proof. Number one, suppose that G is cyclic, generated by A, right? And suppose H is a subgroup. Suppose that H equals to E is cyclic. Well, suppose if H is equal to E, it's cyclic, so we're done. So we'll assume that H is not equal to the identity group in what follows. Consider, if a to the k is an element of H, then a to the minus k is an element of H because H is a subgroup, which is closed-ended inversion. So a to the k times a to the minus k is a to the 0, which is equal to E. Let's let lambda be the set of powers which a to the n is in H. Since this is a subset, a non-empty subset of the natural numbers by the well-ordering principle, there exists a smallest element. Let T be that element. We in fact can expect that we can argue that H is generated by a to the power T. Let's see how that goes. So, since a to the T is an element of H, it follows that a to the T to the S is an element of H for S and Z by closure of the group operations on H. Thus, the subgroup generated by a to the T is a subset of H. Suppose a to the K is an element of H. By the division algorithm, there exists Q and R and Z, for which K is equal to QT plus R, where R is between 0 included and T not included. Observe that a to the power K is a to the QT plus R is a to the QT times a to the R by laws of exponents. And then this implies, of course, that a to the R is equal to a to the, multiply both sides by a to the minus QT times a to the K, like that. But note that a to the T is an element of H implies that a to the minus QT, right, which is, by the way, a to the T to the inverse to the Q, is an element of H. Thus, both a to the minus QT and a to the power K are elements of H, which then implies, of course, that a to the R is an element of H. Right? Thus, R equals to 0, as T was the smallest element of lambda. Therefore, in fact, we have that R was 0, so K was equal to QT, hence a to the K is a to the T to the Q, which is an element of a to the T. Thus, H is a subset of the subgroup generated by a to the T, which allows us to conclude, of course, that H is equal to the subgroup generated by a to the T. Indeed, H is cyclic with generator a sub T as claimed. That brings us to page 14, my unending handout. So continuing our proof of the fundamental theorem of cyclic groups. So suppose that G is generated by A and that the order of G is n, H is a subgroup, the order of H is K. Following the proof of 1, we know that there exists a generator for this H, but we can also observe that a to the T to the n is a to the n to the T, is e to the T, which is E, and observe that a to the T has a to the T to the n equal to E, and H, thus, Corollary 1.6.14 provides that the order of a to the T must divide n, which is to say that K divides n. There we go. So this little paragraph replaces the, again, we know this result by Lagrange's theorem, but this argument's self-contained, which is kind of nice. Now, 3, suppose that we have a positive divisor of n, then our theorem 1.6.15 provides that the order of the subgroup generated by a to the n over k is equal to n divided by the greatest common divisor of n with n over k. But that is just k again. Hence, the subgroup generated by a to the power n over k is a subgroup of order k. And suppose you had another subgroup of order k, then by the proof of 1, we know that there exists a generator for that other subgroup, and we also know that t is a divisor of n, and that, well, consider t is the greatest common divisor of t and n, and by theorem 1.6.15, k is equal to the order of a to the t, which is equal to the, t is equal to this, right? So it's equal to the order of that, which then by our theorem is n over GCD that, which is n over t. Therefore, t is equal to n over k, and we conclude that the unique subgroup of order k is precisely h to the n over k, right? Because if we take another subgroup of the same size, we're led back to the same subgroup once more. So there you go. That's the fundamental theorem of cyclic groups. It's not like, it's pretty easy actually to learn. I mean, as a student, if I was asked to prove it on a test, I might find it a little bit terrifying if I wasn't expecting it. But if I was to ask you to prove that, I would ask you to prove it. All right? Come on. I'm not a monster. All right, theorem 1.77 in my notes. Let G be a cyclic group of order n. If D is a positive divisor of n, then phi of D is the number of elements of order D in G. So here's the proof. By theorem 1.575, is cyclic with order D. By theorem, this sentence isn't quite right. Suppose you have a group of order n, which is cyclic. Then by theorem 1.75, if D is a positive divisor n, then there exists a unique subgroup of order D, and that H is equal to A for some, it's generated by A for some A and G, and of course the order of A is D. But we also learned that the subgroup generated by A is equal to the subgroup generated by A to the k, if and only if the greatest common divisor of k and the order of the group, which here is D, is equal to 1. So the number of distinct choices for k is exactly phi of D. Therefore, the number of elements of order D is precisely phi of D. So super useful. You want to count the number of elements order D in a cyclic group. You just got to go, what's phi of D? So for example, if you have G as a cyclic group of order 19 times k for any k you like, okay, well then 19 divides n. I'm saying this is n. Well, 19 divides n, and we find that there are phi of 19, namely 18, because 19 is prime, right? So 19 minus 1 is 18. Elements of order 19. And it doesn't matter if you're in Z19 or if you're in Z19 million, there are still 18 elements of order 19, so phi of D gives it to you. Now this argument here is a little bit off the beaten track a bit, but maybe worth our time. In a finite group, the number of elements of order D is divisible by phi of D. So here I'm not assuming that the finite group is cyclic, but here's the argument. If G is a finite group and G has no elements of order D, then phi of D divides 0. Okay, great. Otherwise, suppose G has an element of order D, say A. Well, then the group generated by A has phi of D elements of order D by theorem 1.77. Next, suppose that B is an element of G, that the order of B is D, but B is not in the subgroup generated by A. Well, once more, B has phi of D elements of order D, right? The subgroup generated by B. And notice that if you did have an X which was common to both the subgroup generated by A and subgroup generated by B, where the order of X was D, then, well, the order of A would be equal to the order of X, which would, the subgroup generated by A would be equal to the subgroup generated by X, would be equal to the subgroup generated by B, which would then say that B is an element of A, which contradicts our assumption. So thus we can rightly assume that the subgroup generated by A and the subgroup generated by B are distinct. And so after finding the second thing, we count twice the phi of D elements of order D. But this is a finite group, so this you can continue this process until you exhaust the number of elements of order D, and you can see that in fact there are multiple of phi of D. And so that's something we'll see in finite groups. If you look for elements of order D, and it's not a cyclic group, you still know something. You still know the number of elements has to be a multiple of phi of D. So it's not just the Wild West. It can't just be any number. It has to be a multiple of phi of D. I might have an example of that here. Let's see here. 16. So U20. U20's got these guys, these bad boys in here. Let's see here. For example, 9 has order 2, 11 has order 2, 19 has order 2. So order of 9, order of 11, order of 19, all 2. So there are 3 subgroups of order 2. Well, for one thing, that tells us that U20 is not cyclic, right? And you can check, let's see here. What else am I doing here? I'm showing you that the order of 3 is 4, the order of 7 is 4. So I'm looking at powers of 3 and powers of 7 to see how long it takes back to cycle back. I should say circle back in this. Or we passed, we're after Afghanistan, we don't talk about circle back anymore. Let's see here. So, bigger fish to fry, I suppose. Now we're tyrannical states of America too. That whole thing's going on right now. A little kind of cutesy cute. Don't have a president anymore. Have a dictator. There's a little that little thing. But anyway, fun times. Anyway, I digress. Sorry. It's the pneumonia talking. Anyway, so here's the order of 3 is 4. So basically, you just look at powers of your elements, right? And when they cycle back, you can tell the order. So 3, 7, 13, and 17, these are all, by explicit calculation here, modulo 20, they all have order 4. So you can see that the previous theorem in action here. Phi of 4, of course, is 2, and there are 2 times phi of 4, namely 2 times 2, which is 4 elements of order 4 inside U20. So this illustrates corollary 1.79, in case you're wondering. All right. Where was I? 16, 17. Direct products of groups. So this brings us to our next large story arc. This is a pretty good place for me to stop and eat breakfast. So I'm going to stop here, and we'll pick it up again right here. Thanks, guys.